You know how you get those real-time ride updates, or live sports scores, or instant notifications from your bank? Well, a lot of that magic is powered by a technology called Apache Kafka. Okay, so let's dive in and explain exactly what this thing is and why it's become the absolute backbone for so many companies.
To kick things off, let's just start with a number that really puts Kafka's impact into perspective: 80%.
That's right. Over 80% of Fortune 100 companies rely on Kafka. So what's the big deal? What problem does it solve that makes it so indispensable?
To really understand Kafka, we're not going to start with some super complex technical definition. No. Instead, we're going to use a simple, relatable example. Imagine this. We're building a site to show live updates for soccer matches. Every time a goal is scored or a substitution is made, we want it to pop up on our website instantly. So, in a very simple setup, we'd have a reporter at the game, let's call them the producer, who sends an event like "goal" into a single message queue. On the other end, you've got our website, the consumer, which just reads from that queue and updates the page. Simple, right? And for one game, it works perfectly. Yeah, but this is where things start to get tricky. That simple approach completely falls apart the moment we need to scale up. So what happens when we're not tracking just one game, but hundreds of games, all kicking off at the same time? That single queue gets totally overwhelmed and we've hit our first major roadblock. And this, by the way, is exactly the kind of data integration nightmare that LinkedIn was facing when they first created Kafka. The old way to solve this was to create these custom point-to-point connections between every single data source and every service that needed it. The result is, well, it's what you see here, an unmanageable, tangled web of integrations that's just impossible to maintain. So, how does Kafka bring order to all this chaos? Well, it does it with a much more elegant solution. Instead of that messy web, Kafka acts as a central distributed streaming platform. All the producers, like our game reporters, write their events to Kafka, and all the consumers, like our website, read from Kafka. This completely decouples the writers from the readers. It's a game changer. Now, to keep things organized, Kafka uses topics. A topic is really just a logical category for messages. So we could have a soccer topic for all our soccer game events. And if we expand later, a separate basketball topic. Easy enough. Okay, but hold on. This brings up a new question. If all the soccer events are just pouring into one topic, how do you make sure that a goal in the 80th minute is processed after a foul in the 75th minute for the very same game? All of a sudden, we've lost our guarantee of order. The answer is partitions. And what's really clever here is that partitions solve both the scaling and the ordering problems at the same time. A topic is split into multiple partitions, and you can think of each partition as its own perfectly ordered log file. So here's the crucial part. How does Kafka decide which partition a message goes to? Well, when our reporter sends an event, they include a partition key. In our case, the game ID. Kafka takes this key, hashes it, and uses that to consistently pick a partition. This means all events for Brazil versus Argentina will always land in the exact same partition in the exact order they were sent. Problem solved.
So let's be crystal clear. A topic is just a logical label for organizing your data, like soccer. A partition is the physical log on a server that actually stores the data and allows you to handle that massive scale.
We've solved the producer scaling problem and the ordering problem, but now we have a new bottleneck. With thousands of events pouring in, our single website consumer is like someone trying to drink from a fire hose. Just can't keep up. The solution here is the consumer group. You can group multiple consumer instances together to work as a team. Kafka intelligently distributes the topic's partitions among the members of the group, guaranteeing that each message is processed by only one consumer. This allows you to scale your processing power just by adding more consumers to the group. So Kafka is scalable, but what happens if a server crashes? How does it make sure your data isn't just lost forever? Well, that's where durability and fault tolerance come in. See, your data isn't stored on just one machine. Each server in a Kafka cluster is called a broker. A partition's data is replicated or copied across several brokers. For any given partition, one broker acts as the leader, handling all the reads and writes. The other brokers are followers, and they just copy the data. Now, if the leader fails, one of the followers is automatically elected to become the new leader. This is how Kafka stays highly available. Okay, let's pull back and look at the big picture. We've just covered a lot of the core mechanics. So let's revisit that really technical definition from the beginning. An open source, distributed, durable, very scalable, fault-tolerant pub-sub message system. Now, every single one of those words should make perfect sense.
Distributed, durable, scalable, fault-tolerant. We now know exactly what those mean in the context of Kafka.
But Kafka is even more than that. It's often called the Swiss Army knife of data because it's a whole ecosystem. You have the core messaging system we just talked about, but also Kafka Streams for processing data on the fly, and Kafka Connect for easily pulling data from or pushing data to other systems like databases.
So here's the crucial takeaway. Kafka fundamentally changed how companies handle data. Instead of building these fragile, custom pipelines between every system, it provides a central, reliable, real-time backbone that any service can tap into.
This whole shift from processing data in slow, overnight batches to processing it as a continuous, real-time stream has unlocked incredible innovation. And it leaves us with a final thought. As our world gets even more connected and more real-time, what's the next big, complex challenge that will be solved by thinking in streams?